Ilaria Zappatore with this talk about algorithm-based fault-tolerant techniques. Thank you, Ilaria.
Thank you for the presentation, and thank you to the organizers to giving me the opportunity to present my work here. It's a great pleasure for me because it's an Italian conference and I'm Italian. So today I'm going to present the work that I did in collaboration with Eleonora Guerrini and Romain Le Breton about an application of error correcting codes, which is slightly different compared to the application we are used to. So which is about the construction of an algorithm resistant to faults, to computational errors. So we start by giving an overview of the motivations behind this work. So basically, high-performance computing technologies, also known as supercomputers, as the word suggests, are very strong computers, which allows us to complete heavy computations. And they can be modeled as a main node connected to several computing nodes. The problem is that these kind of computing nodes could make some mistakes in the computations. And the bigger the number of components of the system is, the more these kind of errors become relevant. So it arises the problem of construct algorithms which are resistant to this kind of computational errors introduced by the nodes. And in particular, in the work that I present you today, we apply an algorithm-based fault-tolerant technique. And in particular, we consider the algorithm, we apply a transformation inside the algorithm. So basically, we first add redundancy, we perform a sort of encoding inside the algorithm, and then we modify it in order to work on encoding data, and we perform a sort of error correction inside in order to make it strong, robust to the computational errors. So these two are the two basic principles of error correcting codes, adding redundancy and perform an error correction, which, as we have seen, as I told you in the beginning of the talk, which we apply in another context, which is different from the classical communication scenario. So in particular, in the work that I present you today, we apply this technique for the resolutions of systems of linear equations with polynomial coefficients. And in particular, we apply this technique to the classical evaluation interpolation technique. Why we choose this technique? That's basically because this technique can be easily parallelized to this distributed scenario. And also because we can adapt some techniques of decoding of some important error correcting codes in this kind of algorithm. And this work was first introduced in a paper of 2014 by Boyer and Kaltofen, and then developed in another more recent paper in 2017. And today I present you some results of these two papers, of a paper of 2019, which we presented at ISIT, and a paper of 2021, which we presented at ISAC. Okay, so let's take a look inside the problem. So what we want to do is to solve a system of linear equations, a square system with polynomial coefficients over a finite field. And we assume that the matrix A is full rank. So under these assumptions, this system admits a unique solution, which is a vector of rational functions with the same denominator. So our goal is to find this solution. And in order to do it, as we have seen at the beginning, we apply the evaluation interpolation technique, which we adapt to a distributed environment, in which we assume that any computing nodes first have an evaluation point over the finite field. It first computes the evaluation of the matrix A and of the vector B, and then it computes the solutions of the evaluated systems that they get. So they basically compute, each node basically computes the evaluation of the vector of rational functions that we want to reconstruct. Then the nodes send to the main node all these evaluations, and the main node performs a sort of interpolation in order to reconstruct the solution Y. But as we have seen in the beginning, we assume in our model that the computational errors make some mistakes. And in particular, we assume that the introduction of errors happens after the second step of the algorithm. So the nodes could compute wrong evaluations of the solution of our problem. So we can modify our classical algorithm in order to make it robust to errors. And how do we do it? We add redundancy, which in this context means that we consider more evaluation points compared to the number we had in the beginning. And then the main node takes all the evaluations, some of which are erroneous, and performs an error correction, a decoding step, in order to reconstruct the solution of the system. On this third step here, because it's here that we perform the decoding, the error correction, and this problem is called simultaneous Cauchy interpolation with errors. So formally, this is the problem of reconstructing a vector of rational functions with the same denominator d by its evaluations, some of which erroneous, and given also two upper bounds on the degree of the numerator and the denominator, and an upper bound on the number of errors. And what we will see is that in order to solve this problem, what we will do is to apply a generalization of the classical Welsh-Berlekamp decoding technique for decoding Reed-Solomon codes. Okay, so at this point, there are two important questions which are at the basis of this talk. The first one is how many evaluation points, or in this context, how many nodes we need to uniquely reconstruct the solution. Means reducing computations can reduce this number as much as possible. So here you can follow the outline of the talk. We complete with all the existing results in the literature in black and with our new results in purple. In particular, we will complete this table with all the number of evaluations needed to reconstruct the vector of rational functions in the general case. And what we first remark is that if we want to reconstruct, instead of a vector of rational functions, a vector of polynomials, what we have is the problem of decoding a variation of Solomon codes, the interleaved version of Solomon codes. So we first now speak about these codes. So basically, interleaving is a construction that we can apply to any code in general. Here we apply it to Reed-Solomon codes, and this construction allows to correct what we call burst errors, errors on consecutive elements of the code word. So how can we construct a code word in Reed-Solomon codes? The idea is to evaluate a vector of polynomials at several evaluation points. So in this way, we get the code word of an interleaved Reed-Solomon code. We imagine to send this code word in a channel, column by column. And since this channel has the burst errors, errors on consecutive elements of the code, in this model, if there are some errors, the errors affect an entire column of the code word. So the problem of decoding interleaved Reed-Solomon codes is the problem of reconstructing a vector of polynomials by its evaluation, some of which erroneous, and given also an upper bound on the number of errors occurred in the transmission, in the communication over the channel. So this is our starting point. And what we will see is that in order to solve this problem, what can we do is to apply a generalization of the Welsh-Berlekamp decoding technique for decoding classical Reed-Solomon codes. And the idea is to solve, so the decoding problem is to find solutions of this key equation with these 2-degree constraints, because basically, intuitively, we are interested in solution, in a specific solution in order to decode the sent code word. We want to recover this solution here, where lambda is a very important polynomial, which is the error locator polynomial, whose roots are the erroneous evaluations. And once we find the solution of this problem, then we are happy, because dividing the first components by the last one, we get f, which is the vector of polynomials related to the word. So, but now we would like to understand the number of errors that we can correct using this technique here. And there are classical results about coding theory in general, which says that if the number of errors is smaller than the error capability of the code, which in this case for interleaved Reed-Solomon codes correspond to this quantity here, or equivalently, if the length of the code is greater than this, then we can uniquely decode the sent code word. Because if we consider the ball centered in the received word and with radius to 0, then there is only one code word inside the ball. So we can uniquely reconstruct the sent code word. And in this framework, related to the technique that we have seen before, this means that the problem of the technique admits a unique solution, which is this one. If we extend the decoding radius, the solution of the decoding is not unique anymore. That could be two code words correspond to the sent word, to the received word, and we are not able to understand which was the sent one. There is an important result about interleaved Solomon codes, which says that if the number of errors is smaller than this quantity, which is greater than this to 0, or equivalently, if the length of the code is greater than this, then we do not have the uniqueness of all cases, but we have the uniqueness for almost all error patterns, meaning that for almost all error patterns in the ball, there is one code word. And according to this result, we are also able to count the proportion of errors leading to non-uniqueness, which is upper bounded by this quantity, which is small, since for this kind of codes, we consider a cardinality of the field, which is big. Okay, so we have seen the decoding of interleaved Solomon codes. So what we do in our papers is to apply this technique for solutions of vector operational functions and solutions of system of linear equations. So basically, the idea is the same. We can apply to solve our initial problem, which is the problem of reconstructing a vector of rational functions by its evaluation. We can apply a generalization of the Welsh-Berlekamp decoding technique and reconstruct this solution here, where again, lambda is the error locator polynomial. And once we get this solution, then we can recover V and D, which is the solution of our initial linear system. So what we do paper is to generalize and revisit techniques of decoding of interleaved Solomon codes to this more general scenario, and prove that with these number evaluations, which is smaller than previous results, we can uniquely reconstruct solution of our problem and for almost all error patterns, and we are also able to count the proportion of error patterns leading to non-uniqueness, which in this case is upper bounded by this quantity, which now depends also on the degree of the upper bound on the degree of the denominator. Okay, so we have completed our table, and we can now draw conclusions. So just to synthesize what we have done, we introduce an algorithm which allows to solve systems of linear equations with polynomial coefficients in the case in which there are some errors after the evaluation step of the evaluation interpolation technique. And these kind of errors are introduced by using nodes. And we managed to get something which allows us to reduce the number of evaluations compared to previous results in order to reduce computations. There are several problems which are related to this work. The first one is we would like to better estimate the failure probability, the count of the number of errors which we can uniquely correct. And we would like to prove that this quantity is independent on the number of errors, as for interleaved Solomon codes. Because as we have seen before, we had something which is dependent on the number of errors, so we would like to remove this dependency here. We did some tests which go in the direction of proving this result, but we would like to prove it theoretically. And another interesting question could be, or another interesting research track could be to analyze this kind of codes, because this problem, the problem of reconstructing the vector of rational functions by its evaluation, some of which erroneous, could be seen as the problem of decoding the interleaved version of this kind of codes, which are a generalization of Ritz-Solomon codes, in which we, instead of evaluating polynomials, we evaluate rational codes. So we would like to better study these codes, starting from there, the determination of parameters, and understand if there are other applications beyond the one that I presented today. And another open question is related to the possible reduction of the number of evaluation points needed to reconstruct the solution. Can we further reduce this number? And the answer is we don't know, but we can use some of the techniques of this paper, which is related to another general problem, to improve this result and to further reduce the number of evaluations. So thank you very much for the attention. If you have any question, I'd be glad to answer. And just to second for a sort of advertisement, in November, if you are interested in this argument, in this topic, in November I will do a longer seminar about these topics, and I'll explain better the technical results and so on. So thank you very much.